So in the last video, we saw a simple example of how machine learning could potentially learn the correct parameters, in our case, m and b for the y equals mx plus b equation, to find the line of best fit through the cloud of points that we generated synthetically. And the thing is how do we know this is the line of best fit? Well, we saw all those residuals, all those errors that in the model's predictions, the difference between each one of those points and the line that was making the predictions that our model generated with y equals 2x plus 1 and all the other ones that we tried. How do we know which one's better than another? Is that we have to decide how to calculate the error of our model. And there's many different functions that we can use to calculate the error of our model. In this example, we're going to use mean squared error. And so in machine learning, there's two words for calculating the error of a model's predictions. The first one is the loss function. The loss function is the measure of your the measure of error of your model's predictions on just one example. In our case, for mean squared error, the error on one example is that the actual label, the actual y value that we got in our data set minus y hat, which is our model's prediction. So it's the actual y value minus the predicted y value by our model, and we take that number and we square it. And that's going to be the model's error on that one example, and that's the loss function. So remember, loss function is for one example. The cost function is going to be the measure of error of the model's predictions across all the examples. So as you can see here, we have this yi minus y hat squared, the difference between our model, the actual y value and our model's prediction squared, but we have it summed up across all examples in the data set. This is what I equals 1 to n, the summation operator, is doing, is that it's calculating that squared error on every single example, summing it up across all examples in the data set that your model was used to, your model was trained on, and then it's going to divide it by the number of examples in your data set to get an average. So this sum and division right here is just the average. And so that's why it's called mean squared error, because mean is average and squared error is this squared error term right here. So we're taking the average squared error across the entire data set. So remember that loss function is the error on one example and cost function is the error across all examples. You'll hear them used interchangeably, and in most cases, especially in a social setting where you're discussing a particular loss function or cost function on a model that somebody created, and someone says loss function, just use the context to discern whether they're talking about that measure on one example or across the entire data set. No need to be too technical, but technically speaking, a loss function is on one example and a cost function is across all examples, just so you know. And so let's hop into the notebook and actually see how do we calculate and actually visualize what this cost function looks like, the cost function specifically when we change the parameters of m and b. So here, remember, this is our cloud of points and this is our line of best fit that we thought, right? This is our hypothesized one. M is equal to 2 and b is equal to 1. And these are all the residuals that we're getting from this y equals 2x plus 1 line here. And so we want to do is, first, I have this function right here that's going to compute the mean squared error. It's going to take in the m coefficient, which is 2 in this case. It's going to take in the b coefficient, which is 1 in this example. It's going to take in our x values and our y values, and it's going to compute the mean squared error across the entire data set. That's what this is doing. And so for m is equal to 2 and b is equal to 1, that y equals 2x plus 1, the mean squared error across the entire data set is 82.73. Our question is, now, is that the best? And so we can visualize this cost function across like many different m's and b's, right? So I'm going to create several different m's and several different b's, and I'm going to see what the cost function is for each one of those. And what we get here is this nice convex function, or surface, convex surface. So convex stands for like a bowl shaped, like this looks like a bowl, like a pretty good bowl here. And it's kind of got a saddle point. That's what it looks like, because this one doesn't go out far enough to create that bowl. But it's convex. Concave, you'll see that we don't really work with concave functions here, but concave would be the opposite. And you can think of concave being a cave, as if you flip this upside down, or if you flip the bowl upside down, and this point was up here and it was, flipped. But this is a nice convex function, or convex surface, and that's what you want, because here you can read this like this. If the slope right here is -5, if m is -5 and b is 20, we can go out here and find a point where that would be. We're getting pretty close. And so we have -5.63, that would be m. I know it says x right here on the hover label. 20.7, that's going to be b. I know it's y. And then z is our cost function. This is the mean squared error across the entire data set for these two parameters. So if I set m to be equal to -5.63, and I set b to be equal to, or -5.39, and I set b to be 20.7, I would get a cost function of 2400, which is way higher than the 82.73 that we had. And so as you see, what we're trying to do here is we're trying to find the minimum. See, the minimum is down here. If I can look at it, you see like how its lowest points are down here, and it's more than likely, if it's truly convex, right, it's going to be in the center. And so we can go down here and see we're getting down to 81.801 is actually smaller, and so this would be a better fit. And all these points are the smallest points. These points up here are the largest ones. You get really high cost functions. And so essentially this chart right here shows you that for different m's and b's, for the y equals mx plus b, this is what the mean squared error on our data would be if we varied them along these axes. And what we're trying to do is find an algorithm that no matter where we start here, no matter what m and b we choose, it's going to take us all the way down and find the point of the line of best fit. And we're going to find it, and it's going to be somewhere around here. And so that is going to be the algorithm we're going to learn about next, and that's gradient descent. There's many ways to do that in a very simple linear regression context, but when we go to more complicated settings, especially like deep learning where you have millions of parameters, you're going to want to use gradient descent, and you're not going to be able to calculate it analytically. You're going to have to use a numerical iterative solution like gradient descent. And so that's what the cost function is. We use MSE. It's a measure of error across the entire data set. We even plotted what the cost function would be for several different values of m and b, and we now know that like we're trying to find these parameters of m and b that have the smallest error possible down here in the bottom of this bowl. And that is what gradient descent is going to do for us. And so in the next video, we're going to walk through that algorithm and see how we can use it to learn the best parameters for our data.